So in our 60-second writing for today, as we start our lesson on continental drift and plate tectonics, what evidence did Alfred Wegener have to make his hypothesis that the continents are moving and had once been one giant supercontinent? And then secondly, why was his idea not accepted until about 50 years after his death? So he first proposed this idea in 1910, and it did not become widely accepted until 1960. And in terms of science, this is actually a relatively new idea. When I was even in college, it was just starting to get into the textbooks, which wasn't in the 1960s. That was like 80s, 90s. So, anyway, so with continental drift, who wants to help us out with this question here? And if you look on your worksheet you did, there was this little thing that says types of evidence. There's three major lines of evidence that helped him determine this. So there was fossil evidence, and we'll go over each of those in a minute. So just real quickly, there was fossil evidence. What other kind of evidence was there? Yes. Climate evidence, which actually also ends up being fossil as well, and land features. So we'll go over those in a minute. So if he had all this great evidence that suggested this was true, why did people not really believe him? There's probably two major reasons with this. Yes. Yeah, it turns out he was a meteorologist, a weather scientist, rather than a geologist, and so he was kind of outside his field. And people said, "Look, you're not an expert on this. Uh, we don't want you telling us about rocks." And what's another reason? To support, because he had some evidence. Yes, exactly. He was missing this one big explanation is what force could possibly move continents? Because that's a pretty big deal. So let's go ahead and look. So this, we had this up here yesterday. And you can move the continents and kind of see. The first most obvious thing people often notice is that there's kind of this almost puzzle piece fit. Particularly South America and Africa look kind of like they just fit together like that. But that's, of course, not enough. And as the textbook went over, here are some other things that showed. And again, on that worksheet, here are some of the other things that match up. If you take all the continents and squish them together like this, again, South America and Africa not only fit nicely together, but this, and these are images straight from the textbook, folded mountains. So here's some land features. Land features, if you put the continents together like this, you see things like mountain ranges and rock types, layers of rock that match up on these places that are quite far apart now. Coal beds is another one. Coal is both fossil and a rock type. So this is showing a place with these X's here. So places that those seem to match up. Then we had somebody mention fossils, and the textbook uses this big annoying name, and this was actually on the worksheet. What fossil? And it's the Glossopteris, which I told you a simpler name. What kind of fossil was that? It was a fern. I don't care if you know this name. But basically, on matching coasts, we found fossils of both plants and animals that matched in all these places, which is pretty unusual. And on top of that, here we have ferns and fossil evidence of warm areas in what's now Antarctica. So that's land features, that's climate, and the climate evidence is actually also in the fossils. And what else? We got the other dinosaur fossils, glacial deposits, evidence of glaciers. The one question, which again I thought was a little confusing, scratches in rocks made by glaciers. When glaciers move, huge ice sheets, they leave these very straight, it looks like they're made by a bulldozer or something, carved into the rock. So I thought it was kind of a little bit of an awkward question, but those are some of the lines of evidence. But even though Alfred Wegener and people he worked with came up with all of those lines of evidence, he couldn't really explain what could make the continents move. So what finally years later was discovered that helped us explain what is moving continents. Yes? What do you say? Tectonic plates, but what's making them move? Look on the yes. Okay, so we've got convection in the mantle, but how did they know that was happening? We started exploring the ocean floor, and we found something called seafloor spreading. And so the biggest place this is discovered is actually along the mid-Atlantic ridge, because what we needed is a force that was pushing these things apart. And with sonar images from ships, you could actually see there's a massive mountain range going all along the floor of the Atlantic Ocean. And not only is it a mountain range, but if you look, you could actually see that, and it does go, Iceland is right on top of it, why Iceland is volcanic, which we'll talk about that a little more next week. Yes. So what we see is in this seafloor spreading, it's not just a mountain range, but there's also volcanic activity. So you've got volcanic activity, seafloor spreading, new crust is actually being laid down. So you've got molten material, you could call that lava or magma. We'll talk about that next week. Magma is just lava that hasn't come to the surface yet. So it seems to be pushing up here and making new crust. Like, okay, well, how do you know it's really making new crust? Well, do you guys remember the line of evidence that's showing that it really is pushing the crust apart here? It's actually really cool. They found, so a lot of volcanic rock is has a lot of iron in it. Iron is magnetic. And so this is a little crazy, a little confusing, but they actually found, so if you got the North Pole, I've got this all drawn on here already. If you got the North Pole and the South Pole, if the iron-rich rock is melted, then the charged particles in the rock line up with that. So here's the South Pole, here's the North Pole, and so we'll just make the North Pole positive and the South Pole negative. So then all of the ions in the rock are going to line up like this, so that they line up with the magnetic poles. And then we discovered, and this is really weird, but over time, over millions of years, the magnetic poles actually switch. They move over a little bit, so the North Pole might move over here. But we also have evidence now that in the history of the Earth, at some times, this one has been north and this one has been south. And we know that because of the rock record, right? The way the magnetic fields in the rocks are, because once it cools, it's preserved. But then most importantly, you found out, well, right here, it's oriented this way. And in this strip of rock, it's oriented this way. And then here, it's like this. And so these are equal distance away from the mid-Atlantic ridge, proving that it is, in fact, making new crust and pushing it outward. So that's a little confusing, but we basically have two things going on here. One, we can take dates of this rock, and this rock here is the same age as this rock, and then we can see that the magnetic striping matches up. That's a lot of information. But what you need to remember is, what evidence did they finally find to support Alfred Wegener? Seafloor spreading. So new rock is being added to the mid-ocean ridge, and we can prove that through the magnetic stripes in the rocks and the age of the rocks. So through this, then we start coming up with what a couple of you mentioned. Then we can start thinking about, well, so maybe these are pushing apart. And since they actually found this mid-Atlantic ridge, this mid-ocean ridge right here, and it's pushing South America away from Africa. So this fits perfectly with the idea of which plates might have been together and might be now being pushed apart. And so then once this idea kind of starts to work, then we find more evidence to support that. Okay. looking over what you read yesterday, the hypothesis of continental drift is just that the continents were moving apart. It was a hypothesis, an educated guess. It wasn't a theory because it wasn't proven, and other people weren't able to prove that or support that. When we had all the continents together in one group, it was called Pangea. Pan means all or everything, and Gea is a name for Earth. So all Earth, and when all the continents were together in Pangea, they were up closer to the equator, so Antarctica wasn't as far south, which explains the climate difference. Well, actually, it's not so much this global warming, but it was a big climate difference. And in the time of the dinosaurs, which is not quite this far away, there's things that show the time progression. What happened was we had, in this area here in Colorado, it was very tropical. There is lots of fossil evidence that it was swampy and warm and much more tropical here. And part of it is climate change over time, but part of it is because look how much closer to the equator it is now than when it's moved up here where it is, here versus where it is now. So part of the climate difference in the time of the dinosaurs, 65 million years ago, is that the continents were actually in different places. So yeah, a little bit different than global warming, but definitely climate change. Okay, and so mid-ocean ridges are existing in other places as well. But if we have new crust being formed and pushed apart, then is the Earth getting bigger or is it getting wrinkled? What's happening to the rest of that crust? You can't just keep making more and more and more. What's that? It has to melt somewhere else. It has to be destroyed somewhere else. And so what we have here is a nice image showing, so when we get the whole theory of plate tectonics that the plates are moving, you have new crust being formed here, right? And it's being pushed and pushed and pushed and pushed. Then somewhere else it has to be destroyed. And so over here, we have older oceanic crust. So they're showing the evidence. And then it gets pushed under another piece of crust. And at this place, we have continental crust, which is in a continent. And then we have oceanic crust, which is thinner and denser. We talked about that a tiny bit, right? The thinner, denser, and then the less dense. But that's going to come into play here. So let's talk about the types of plate boundaries that we see in plate tectonics. So here's the plates that we've been able to identify based on movement we see. And we can come back to that in a minute. Here are the three types of plate boundaries. So let's take a look here. These are nice and logical, right? Because they have nice logical names. It's always nice when scientists use things that make sense. We can have a divergent boundary. To diverge means to move apart. So a divergent boundary is when plates are being pushed apart. It would be good if you jot this down or draw it. On the second part of the worksheet you did yesterday, you have these images, which is what we're talking about now. So you can just add to this or put this with it. So a divergent boundary, the two plates are being pushed apart. And just like at a mid-ocean ridge, why are they being pushed apart? Usually because of new crust being formed. This is what's called a constructive boundary because new crust is being formed. And this can happen in two different ways. It can happen at a mid-ocean ridge, like we just talked about. Or, this is obviously oceanic. Does anyone know what it's called if it happens in the middle of a continent? Yes. A rift valley. Very good. Rift valley. There's one very famous rift valley on the Earth. Does anyone know where it is? No, not a bad guess. Yes? What were you going to say? Yeah, good guess. No, she guessed a canyon also. No, it's actually called the, yes? It is, and it's actually called the African Rift Valley. Craziness. I know. These silly scientists and their silly names. So it's actually called the African Rift Valley. And I'll pull up Google Earth here in a minute. We'll look at some of these. But there's another one. This is weird that you'd never know it was there unless you studied it. Actually, part of the Rio Grande Valley, like in New Mexico, is a rift valley, which you'd never know because it doesn't really look like it. Okay, so then we have convergent. Uh, Convergent plates are going to be moving together, right? Moving together, that's easy enough. And they're moving together usually because they're being pushed apart somewhere else. We're actually going to have two types of convergent boundaries. You can have, for convergent boundaries, you can have, actually, let's come back to that one because transform's easier. And convergent's going to take us a little more space. So transform is going to be when the plates are moving side by side. Okay? So this one's moving this way. This one's moving this way. Does that look like something we studied before? Yeah, what's it look like? It looks like shearing. It looks like a strike slip fault. It's exactly what it is. The San Andreas fault is not only a fault and shearing stress, it's a transform boundary between two different plates. So plates move side by side, and this crust is not created or destroyed. Crust not created nor destroyed. Okay, so then let's skip to our convergent boundary where plates are going to move together and then we do actually sometimes destroy some crust. Okay, so we just talked about that one. Convergent. And okay, here we go. So there's two types of convergent boundaries. Convergent meaning coming together. If you have continental, which is just the continents, continental crust smashing into continental crust, they're roughly the same density. They're smashing into each other. And so what happens is they make mountains. Okay? So mountain building happens, and you get mountain ranges like the Himalayas we were talking about, where India is smashing into Asia, continental, and it's making a huge mountain range. And then the other, probably most interesting boundary, I think, and the most destructive one as well, is one called subduction. And that's when you have a continental plate smashing into an oceanic plate. And so this one is less dense, this one is more dense. And so what happens, the more dense oceanic one gets shoved underneath the continental one, and not only destroyed, whoops, no idea how I just did that. That's okay. But it gets destroyed, and then you also end up with very big earthquakes and volcanoes and stuff here. Remember when we were watching the worst earthquake things and we were talking about the subduction zone and you saw the pictures of that? That is what's happening. And so here is a good picture of the subduction zone. This is the oceanic crust being pushed under, and as it gets pushed down into the mantle way over here, you actually have a lot of pressure buildup and melting, and so then you'll get volcanoes here, inland from this. And this is what we see along the Pacific Northwest, in Japan, and places like this. And you can imagine here too, because of the friction built up, this is where we get huge earthquakes, because if you have, let's see if I can do this on the smartboard, if you have it pushing and pushing, and then when the stress releases, it pops up like this. And so as it moves up like that, you get big earthquakes and then sometimes tsunamis as it pushes up. Okay, so those are our plate boundaries. And you can see here, again, just looking at the whole Earth, some of the different plate boundaries. We'll continue talking about this, and actually I'm going to give you a little project today, which is kind of fun, and you'll get a chance to look at that. All right, let me go ahead and pull up. Google Earth is really cool because we can actually see on satellite images exactly what's going on here. So I will pull up this, and I will pass out your assignment that we're going to look at in just a moment. All right, so let's take a quick look at this. And Google Earth is something that's really fun for you to play on too. We live in a really cool time because with satellite images, we can see so much. Instead of just having to take somebody else's word for it and look at a picture in the book, we can actually look at these things. So let's go over here to, let's see, kind of up here. So this is the Atlantic Ocean, right? Here's South America, and here's North America. And we'll just zoom in here a bit. Zooming in. Computer's a little slow here. Here we go. Thank you. So as we zoom in here, we can actually see this, this mountain range. And as somebody mentioned, if you follow it up, we've got Iceland, which is a very large volcanic area happening right here. Hang on one second. Brag. Okay, so we can look at this and see these images. And let's look at Japan, because Japan's another place we know they've had big earthquakes. So let's go over here to Japan. Look at this, even from way zoomed out over here. You see how dark that is? It's very dark because it's very deep. And it's very deep because as that oceanic trench is crashing into the continental one, it's being pushed downwards. And so it makes a very deep trench right where the more dense is hitting the less dense. So you see all that along there, and this is where we get tremendous earthquakes and volcanic activity and tsunamis and stuff like that. Okay? You might be wondering about the fabulous island of Hawaii, which doesn't seem to be on a plate boundary, does it? Is it on a plate boundary? No. And so Hawaii, as we talk about volcanoes next week, Hawaii is being caused by something else. It's actually a really active place in the mantle that's basically burning a hole through the crust. Okay, so that pretty much summarizes plate tectonics and the types of plate boundaries and continental drift. And what we're going to look at right now, and then spend a little bit of time getting started on, is this project. So take a look at this. Ignore this top part here. Let me see. That's a different one. So basically what you're going to do is it's called build a boundary, and you are going to make a model of one of the plate boundaries and explain where it happens. So take a look at your green sheet, which I will also post, and show you some examples.